Okay, so let's unpack this. Today we're doing a deep dive into, well, something pretty fundamental, chemical kinetics.
That's right.
And the material we're kind of digging into today, it comes from a pretty dense review doc. It's designed for prepping for the joint entrance examination in India, the JEE.
Yeah, a tough exam.
Right. So our mission really is to pull out the core ideas of kinetics from this source. You know, what actually makes reactions tick at different speeds? How is this stuff used? And what specific points does this JE material really zoom in on?
Well, it's interesting because kinetics, it's that bit of physical chemistry asking how fast.
Yeah.
You know,
It's just if it happens.
Exactly. That's thermodynamics. Can it happen? Is it favorable? Kinetics doesn't care so much about that. It cares about the rate, the speed, and the actual steps involved in the mechanism. And the source material even gives a nod to the history. People like Wage and Goldberg, Law of Mass Action, that's way back 1864. And Van Hoff, who actually snagged the first Nobel in chemistry, 1901, partly for his work on chemical dynamics. So it's got deep roots.
Yeah, definitely not new then.
Not at all. But what is maybe surprising, looking at this JEE prep material, is just how wide the applications are. It's not just theory.
Like what?
Well, understanding food going bad, that's kinetics. Or what happens to ozone up in the stratosphere. Crucial stuff.
Right.
And biological systems, enzyme reactions, incredibly complex, incredibly specific kinetics, plus, big industrial processes like making gasoline, catalytic cracking. Kinetics helps optimize all that.
So it really touches a lot of areas.
It really does. So even though this doc is for exam prep, it frames kinetics as this powerful analytical tool with real tangible effects. Think about everyday things. How fast does that headache tablet dissolve?
Or rust forming on a bike.
Exactly. Kinetics helps us get a handle on those speeds, maybe even control them.
Okay, so we get what it is and why it's important, but how do you actually measure it? How do you put a number on speed for a reaction?
Good question. Basically, the rate, the reaction speed. We track how fast the concentration of something changes.
Okay.
So how quickly are the starting materials, the reactants, disappearing? Or how quickly are the products appearing over a certain time?
Right, change over time.
Yeah, we could talk about an average rate over, say, a minute, or the instantaneous rate, the speed right at this exact moment. That's often more useful.
Okay, makes sense. So you measure the rate, what actually makes it change, what speeds things up or slows them down.
The factors. Yeah, the source lays out the key ones. Fundamental stuff. First off, concentration.
More stuff means faster reaction.
Generally, yeah. More reactant molecules bumping into each other, more chances to react.
Yeah.
And for gases, pressure works pretty much the same way as concentration.
Okay. What else?
Temperature. That's a big one.
Yeah.
A really big one.
Like food spoiling faster when it's warm.
Exactly. Turn up the heat. Molecules move faster, they collide more often, and they collide with more energy. So yeah, usually higher temp means faster reaction. Significantly faster, often.
More energetic collisions. Got it. What else is on the list?
Well, the nature of the reactants themselves. Some chemicals are just naturally more reactive than others. Think about their bonds, their structure.
Sure.
And then there's the physical state. Are things solid, liquid, gas? And crucially, surface area, especially if you have reactants in different phases.
Like a solid chunk versus powder.
Precisely. A powder reacts way faster because there's more surface exposed for collisions. Think dissolving sugar cubes versus granulated sugar.
Right.
Catalysts are another huge factor. These are substances that speed things up but don't get used up in the process.
We'll probably come back to those.
Definitely. And even the solvent, the liquid things are dissolved in, can sometimes play a role in how easily reactants can meet.
Okay, so a whole bunch of factors. Now, is there a way to write down mathematically how the rate connects to, say, the concentration?
Absolutely.
Yeah.
And that's where the rate law comes in. It's basically an equation. It links the reaction rate directly to the concentrations of the reactants. Usually each concentration is raised to some power.
Ah, the exponents.
Yeah. And this is super important, something the source really hammers home. You have to figure out the rate law from experiments.
You can't just look at the balanced chemical equation.
Nope, not usually. Only for very simple single-step reactions. For most reactions, the balanced equation tells you the overall stoichiometry, but not how the rate depends on concentration. You got to measure it.
Okay, experimentally determined. Got it.
And that rate law equation includes a rate constant, usually written as K. It's specific for that reaction at a given temperature. And those powers the concentrations are raised to. They tell you the order of the reaction for each reactant.
And the overall order.
Just add up those individual powers. That gives you the overall reaction order.
Okay, so order comes from the experimental rate law. But I've definitely heard the term molecularity too. How's that different?
Yeah, that's a really key distinction. The source highlights this, especially thinking about JEE advanced level questions.
Yeah.
Molecularity is different.
How so?
It only applies to an elementary reaction step, like a single collision event happening at the molecular level.
One single step.
Exactly. And the molecularity is just the number of molecules that have to come together in that one specific step. Could be one molecule breaking down unimolecular, two colliding bimolecular, maybe three, though that's rare.
Okay.
And here's the connection. For an elementary step, the order is the same as its molecularity.
Right.
But most reactions we see aren't just one step. They're a sequence of these elementary steps. That's the reaction mechanism.
Like a chain of events.
Precisely. And the overall reaction order, the one we get from the experimental rate law for the whole process. That's often determined by the slowest step in that chain, the bottleneck.
Rate determining step.
Exactly. So the overall order doesn't usually match up with just adding the coefficients from the balanced equation. And it doesn't really make sense to talk about the molecularity of the overall reaction. Order is experimental, molecularity is theoretical for single steps. That difference is how we figure out mechanisms.
Okay, that distinction is clear now. Experimental order versus theoretical molecularity for elementary steps. So once we have the rate law experimentally, can we use it to predict how much reactant is left after 10 minutes?
Yes, that's the next logical step. That takes us to the integrated rate equation.
Integrated. Okay.
You basically use calculus to integrate the rate law equation over time. What you get are equations that directly link concentration to time.
So you can calculate concentration at any t.
Exactly. Or figure out how long it takes for, say, 90% of a reactant to get used up.
Yeah.
And the exact form of this integrated equation looks different depending on the reaction order, zero order, first order, second order.
Right. The source mentioned those.
Yeah, it covers the main ones. Zero order means the rate doesn't even depend on how much stuff you have.
Really? Independent of concentration.
Yeah. Weird, but it happens. First order means the rate is directly proportional to the concentration of just one reactant. Double the concentration, double the rate.
Okay.
Second order could mean the rate depends on one reactant's concentration squared, or maybe on the concentrations of two different reactants multiplied together.
And these give different concentration versus time curves.
Totally different mathematical relationships, and that leads into half-life.
Right, you mentioned that.
Yeah. 2½ It's simply the time it takes for the reactant concentration to drop to exactly half of what you started with.
Okay, seems straightforward.
It is, but here's the really cool part, and the source flags this as important for identifying order. How the half-life behaves tells you the order.
How so?
For a zero-order reaction, the half-life actually gets longer if you start with more reactant. It's proportional to the initial concentration. Okay.
Okay. More stuff takes longer to have.
Right. Now, for a first-order reaction, the half-life is constant. Doesn't matter how much you start with, it takes the same amount of time to cut it in half, 0.693 K.
Always the same time, like radioactive decay?
Exactly like radioactive decay. That's the classic example of first order. It's a unique signature.
Okay. And second order?
For second order, it's the opposite of zero order. The half-life gets shorter if you start with more reactant. It's inversely proportional to the initial concentration, 1 Ka rho.
Wow. Okay, so just by seeing if the half-life changes when you change the starting amount.
Bingo. You can often tell if it's zero, first, or second order. It's a really neat diagnostic tool.
That is a neat trick. Okay, so that's the math, the descriptions. But what's actually going on, at the molecule level? Why does temperature matter so much? What makes a reaction happen?
Right, moving from the what's to the why. This gets us into the core theories. The main one discussed is collision theory.
Okay, molecules have to collide. Makes sense.
They do. But just bumping into each other isn't enough. Not by a long shot. No. For a collision to actually lead to a reaction, two conditions have to be met. First, energy. The colliding molecules need to smash together with enough energy.
Enough juice to do something.
Exactly. They need to possess energy equal to or greater than a certain minimum threshold. We call that the activation energy, EO.
Activation energy. Okay. The first condition.
The second condition is orientation. The molecules have to hit each other in the right way, lined up correctly, so the parts that need to react can actually interact.
Like puzzle pieces fitting together.
Sort of, yeah. If they hit with enough energy and the right orientation, then they can momentarily form this unstable high-energy arrangement called a transition state or activated complex.
The peak of the energy hill.
Precisely. And from that transition state, it can then fall apart to form the products. So the activation energy is like the energy barrier, the hill they have to get over to reach that state.
Okay, so that's why temperature is huge. Higher temperature means more molecules have enough energy to get over that activation energy hill.
Exactly right. More molecules moving faster, higher kinetic energy, so a larger fraction of the collisions will have EUOU.
And they collide more often too, presumably.
Yes, both frequency and energy of collisions increase with temperature. And this relationship between temperature, activation energy, and the rate constant K is captured beautifully by the Arrhenius equation.
The Arrhenius equation. Heard of that one?
Yeah, it mathematically connects K to EO and the absolute temperature T. It also includes a term, the pre-exponential factor A, which kind of accounts for collision frequency and the orientation factor. It really shows why rates are so sensitive to temperature.
It quantifies that sensitivity.
Okay.
Now, earlier you mentioned catalysts as a factor. How do they fit into this collision theory activation energy picture?
Great question. Catalysts are fascinating. They speed things up, but how? They provide a completely different path for the reaction to happen.
A shortcut.
Kind of. An alternative reaction mechanism, one that has a lower overall activation energy.
They lower the energy hill.
Exactly. They don't change the starting or ending energy levels, just the peak height of the barrier in between. By lowering E rho, way more molecules, even at the same temperature, now have enough energy to make it over the hump.
So more effective collisions happen per second?
Precisely. Significantly faster rate.
Yeah.
And critically, the catalyst isn't consumed in the process. It gets regenerated.
Right. And the source mentioned different types.
It did.
Yeah.
Homogeneous catalysts are in the same phase as the reactants, like an acid catalyst dissolved in a liquid reaction.
Okay.
Heterogeneous catalysts are in a different phase, very common industrially. Think of a solid catalyst surface with gases or liquids reacting on it, like in a car's catalytic converter.
Gotcha. Solid catalyst, gas exhaust.
Yep. And the source document also gets into some finer points, like catalyst activity, just how much does it speed things up? And selectivity, does it steer the reaction towards the desired product instead of side products?
Important for industry, I bet.
Hugely important. And it specifically mentions the amazing specificity of biological catalysts' enzymes.
Mm-hmm.
They're incredibly selective for their target reactions.
Okay, wow. So we've covered quite a bit. Defining rate, the factors like concentration, temp, catalysts, then the math with rate laws, order, integrated equations, half-life, and the why behind it with solution theory, activation energy, Arrhenius, and how catalysts work. Phew.
Yeah, that's the core of it.
And thinking back to the source, this JEE prep material, it seemed like there was a distinction in depth needed.
Definitely. The way it's structured suggests JE main really wants you solid on the fundamentals. Definitions, factors, and being able to plug and chug with the zero and first order formulas, maybe simple Arrhenius calculations.
The basics.
Right. But JE advanced, that pushes much harder. You need to understand the derivations, handle second order kinetics, maybe more complex rate law problems, trickier Arrhenius stuff, and really grasp the theory of the difference between order and molecularity, mechanism ideas, the nuances of catalysis. It demands a deeper conceptual understanding.
Got it. So if we step back and think about the big picture from this dive, what's the main takeaway?
I think fundamentally it's that understanding kinetics gives you control, or at least the potential for control.
Control over speed.
Yeah. Predicting, managing, optimizing chemical processes, whether it's in a lab, in industry, in the environment, even in our own bodies. And realizing that the rate law we measure experimentally compared to theoretical ideas like molecularity, that difference is actually a clue. It helps us figure out the real sequence of steps, the mechanism.
Unlocking the mechanism.
Exactly. And even simple things like how we saw half-life behaves differently for different orders. A2K versus 0.693K versus 1Ka. Those aren't just equations to memorize. They reveal something profound about how the process unfolds at the molecular level.
Right. It's not just math for math's sake.
Not at all. And when you think about it, all those factors, concentration, temperature, surface area, catalysts, they all tie back to influencing either how often molecules collide effectively or lowering that energy barrier they need to cross. It provides a kind of unified way to think about reaction speed.
Makes sense. It all comes back to collisions and energy.
Pretty much.
Oh, really?
Which leads to a bigger thought, maybe for you listening.
Yeah.
Well, we've seen how sensitive rates can be. A small temperature change, adding a catalyst, boom, massive difference in speed. So thinking beyond just optimizing what we already do, could a really deep grasp of kinetics let us design completely new things?
Like new materials.
Yeah.
Or processes.
Yeah, maybe materials that form only under specific kinetic control,
Yeah.
or hyper-efficient ways to tackle big problems, like cleaning up pollution or generating sustainable energy, just by mastering reaction speeds and pathways. What part of this dive really stuck with you? What makes you want to dig deeper?